The greatest mystery of our planet, the origin of water. Where did Earth's water come from? Our planet is the only one we know of so far that can support liquid water on its surface. With over 2/3 of its surface covered by vast blue oceans, water is likely a key element for the emergence of life. But then, the question arises, where did all this water come from? At first glance, this question might seem straightforward, given the abundant presence of water on our planet, on the surface, in the atmosphere, and even in places you might not expect. Water is so common and vital to our daily lives that it's astonishing when we realize that the answer to its origin isn't so simple. In fact, no one is entirely sure, and the theories we have are complex. And by complex, I mean that understanding a variety of different aspects about Earth's history and the solar system is required to begin to grasp the modern responses to this question. Along the way, we might even find out why gas giants like Jupiter are so much larger than rocky planets like Earth. Why is the origin of water so controversial? The question of how water came to be on Earth sparks intense debate and unresolved controversy. In our solar system, there are two main types of celestial bodies orbiting the Sun: asteroids and planets. Theoretically, since both occupy the same region of the solar system and were formed from similar processes, they should differ only in size. The process that created asteroids is the same one that led to the formation of planets. The key difference is that planets accumulated much more matter, including numerous asteroids. Thus, at their core, planets and asteroids are made of the same stuff, or to put it more poetically, from the same stellar dust. Yet, an intriguing question arises: while planets have water, the majority of asteroids do not. Planets are like oases in a desert of rocks. Even Mercury, the planet closest to the Sun, has water in its permanently shadowed regions. If rocky planets were formed from the same material as asteroids, how come planets have water and asteroids do not? A natural hypothesis that emerges to answer this question suggests that asteroids once had water at some point in their history. However, they would have lost this water because they do not possess an atmosphere or sufficiently strong gravity to retain it. This explanation paves the way for understanding not just how water is distributed in the solar system but also the processes that can lead to its presence or absence on different celestial bodies. However, as we delve deeper into our understanding of planetary system formation, it becomes apparent that the situation might not be so straightforward. During the formation of the solar system and its planets, it's believed that solar radiation would have evaporated and expelled any water molecules in the region where Earth formed, including the water on our planet itself. Only beyond 3 astronomical units (AU) from the primordial Sun does the radiation weaken enough to allow water to condense and accumulate on asteroids and comets. To put this into context, 1 astronomical unit is the average distance between Earth and the Sun today, and 3 AUs are roughly between Mars and Jupiter. Based on our current understanding of the solar system's history, there was no water in the region where Earth was formed about 4.5 billion years ago. This raises an intriguing mystery: Earth, brimming with water, formed in what would be equivalent to a cosmic desert. Both the current layout of the solar system and its history suggest that Earth's water must have come from somewhere beyond the asteroid belt. One of the earliest hypotheses about the origin of Earth's water points to the most obvious source of water in the solar system: comets. These ice asteroids orbit the Sun beyond the gas planet's orbits, far away. Occasionally, these comets intersect with the inner rocky planets. One of the most famous examples is Comet Halley. there is always a chance of a comet colliding with a planet, depositing its water as a result. Thus, the comet theory as a source of Earth's water proposes a fascinating scenario in which Earth could have received its water through impacts with these icy bodies from the depths of the solar system. Moreover, in the primordial solar system, there was a much larger amount of material available in comets and asteroids, making impacts between these bodies and the planets much more common. Therefore, the idea that comets deposited water on Earth after its formation, in a process that would have lasted at least a few 100 million years, gained traction. Interestingly, there is water on the Moon, and what's most fascinating is that the composition of lunar water is almost identical to that of Earth's. And no, I didn't put it there, joking aside. We know this because hydrogen, a constituent element of water, exists in two main forms: regular hydrogen, with one proton in the nucleus, and deuterium, a hydrogen atom with one proton plus one neutron in the nucleus. Water is made up of two hydrogen atoms for every oxygen atom. By measuring the ratio of regular hydrogen versus deuterium in water, we obtain a sort of water fingerprint that indicates its source of origin. The ratios of deuterium in the water on Earth and on the Moon are identical, suggesting a common origin. This implies that when the Moon was formed, Earth already had most of its current water. Considering that the Moon was formed about 100 million years after the planet, Earth must have had all its oceans by that time. This time frame is relatively short for the hypothesis that Earth's water was predominantly deposited by comets. Moreover, mineral evidence on Earth suggests that the oceans are almost as old as the planet itself. There are specific types of minerals that can only form in the presence of water, such as pillow lava, and some samples of these minerals are nearly 4.3 billion years old, which is almost the age of Earth. Therefore, the history of water on our planet is inherently linked to Earth's formation and evolution, presenting a puzzle that continues to challenge our understanding. Furthermore, when comparing the deuterium ratio in Earth's water with that in comets, we notice a significant difference. This detail indicates that most of Earth's water likely did not come from comets. Adding another layer to this discussion, recent studies suggest that most of the water on our planet is found in rocks within the Earth's crust and mantle, in the form of hydrated minerals. Hydrated minerals are stones that incorporate water into their mineral composition, a kind of water in stone. It's quite probable that the oceans represent only a fraction of all the water available on our planet, and that most of it is stored in hydrated minerals. If most of Earth's water is indeed trapped internally, this means that Earth acquired its water during its formation, in a period when, as we've seen, the solar system was supposed to be inhospitable and dry. So, we find ourselves asking again, where did Earth's water come from? Although we still don't have a definitive answer, recent research points to an intriguing and, why not say, surprising possibility. Let's explore a recent hypothesis regarding the origin of water on Earth, the possibility that it came from asteroids. Yes, I just mentioned that asteroids are dry, but here's the twist: not all asteroids are completely devoid of water. In fact, asteroids located at the far ends of the asteroid belt possess some water, especially in the form of hydrated minerals. While these minerals contain water, they certainly aren't a drinkable liquid source. Interestingly, the Japanese spacecraft Hayabusa visited the asteroid Ryugu, hoping I'm pronouncing that correctly, and brought back about 5 grams of material to Earth. Among this material, hydrated rocks were found. It's important to note that during the formation of the solar system, Asteroids were much more abundant and were spread out in a region far enough from the Sun where they could accumulate significant amounts of water. Therefore, water existed in the solar system abundantly in regions 3 times further from the Sun than the Earth. But how did this water end up here? The theory suggests that water could have been transported toward the inner solar system, but not necessarily through the water-bearing asteroids themselves. To explain this, we need to understand that ice has a greater capacity to adhere than rock during asteroid impacts. When 2 rocky asteroids collide, they break apart, generating dust and debris. On the other hand, water can evaporate, be expelled from the hydrated minerals, and quickly freeze on the asteroid's surface during the impact. Because of this property, water was very efficient in accumulating during the formation and collision of objects in the solar system. This ability to accumulate water might even be one of the reasons why gas giants like Jupiter are so vast. They captured large amounts of gas and, possibly, water during their formation, contributing to their enormous size. Thus, against all expectations, it seems that the modest asteroids, especially those enriched with hydrated minerals at the edges of the asteroid belt, could have been the water deliverers to Earth, playing a crucial role in creating the habitable planet we know today. The reason asteroids are considered a significant source of Earth's water is based on how and where they formed in the solar system. These celestial bodies originated in a region where water was plentiful. The seeds of these future planets were primarily made of ice, not rock, as is the case with rocky planets like Earth. Ice accumulates faster than rock, allowing gas planets to grow more quickly in the early solar system. They became large enough for their gravity to start attracting even more matter, while the rocky planets took about 10 times longer to accumulate a significant amount of material compared to the gas planets, which had icy seeds. During the formation of the solar system, the scenario was as follows: the Sun had just formed, essentially a cluster of interstellar gas undergoing nuclear fusion and emitting light in the process. Around the Sun, there was a disk of gas and dust, which included water. This disk was constantly illuminated by solar radiation. Very close to the Sun, water would turn into vapor and be pushed away by the radiation pressure, especially true before the Sun had stabilized and cooled down a bit. As the dust disk spun, dust collided with more dust, and particles joined together, forming asteroids and protoplanets. After a few million years, larger clusters of matter existed, and the seeds of future planets as well. Asteroids that were far enough away from the Sun could retain significant amounts of water, while those closer to the Sun had no water. Thus, the idea that asteroids contributed to Earth's water supply is linked to this initial distribution of water in the solar system, and the ability of asteroids farther from the Sun to retain water during their formation, playing a crucial role in delivering water to the inner planets, like Earth. The origin of Earth's water. At this point, we can clarify how this water arrived on Earth. Water-rich asteroids didn't directly fall onto the forming Earth, as the distances were vast. Instead, these asteroids collided with others closer by, transferring some of their water to them. Some of these now water-bearing asteroids were closer to the Sun than the originals. This second layer of water-bearing asteroids could then transfer some of their water through collisions to asteroids in a third layer even closer to the Sun. Through a series of collisions, water was gradually transferred to the inner parts of the solar system where Earth was forming. Thus, water reached Earth by hopping from asteroid to asteroid until it reached those that accreted to our planet during its formation. In other words, water was transferred from impact to impact until it arrived on Earth. We've observed this phenomenon in the Ceres crater, the largest object in the asteroid belt, where water was deposited by impacts. These types of water-transferring impacts were likely more common in the nascent solar system. Incorporating this into a model, the hypothesis of water transfer by impact accurately predicts the water concentrations we observe on Earth today. But even with this information and a model that seems to work, we notice that Earth has far more water on its surface than other planets in the region. This is due to Earth's atmosphere, which is suited to retaining water on the surface. The temperatures on the planet have never been extreme enough to cause water to evaporate in large quantities, as happened with Mercury and Venus. When water evaporates, it's possible for the molecule to break down into oxygen and hydrogen, with hydrogen being so light, escaping the planet's gravity. This effect does occur on Earth. The oceans likely had about 20% more water in the past than they do today. They are slowly evaporating back into space. This journey of water, from the edges of the solar system to our planet, illustrates not just the complexity of planetary formation but also the uniqueness of Earth, a blue oasis capable of sustaining life as we know it. This video serves as a reminder that we are on the frontier of science, exploring a relatively recent hypothesis about the origin of water on Earth. Our understanding of this topic might evolve in the coming years. After all, science is precisely that, a journey of continuous discovery. We don't always get it right the first time, but that shouldn't discourage us. The quest for truth is not a paved and well-signposted road, it's more like a trail that we need to walk by foot, making our way through the unknown. I hope you felt as fascinated as I have with this scientific adventure, because there's something truly wonderful about discovering something new about our universe. Thank you so much for joining me in this exploration. Until next time.